The cloud has revolutionized how we work and live. Businesses and individuals rely on cloud services for data storage, application hosting, and more. This reliance brings unprecedented convenience, but also significant security risks. Protecting your cloud network is no longer optional, it is essential. Traditional security measures are not enough in the cloud. We need a comprehensive understanding of network architecture, potential threats, and effective defenses. We will explore the fundamental models, best practices, and essential tools that form the bedrock of a secure cloud environment. Our journey begins with the Open Systems Interconnection, or OSI model, a conceptual framework that breaks down network communication into 7 distinct layers. By understanding the functions of each layer, we can identify vulnerabilities and implement appropriate security measures. Beyond models, we will explore practical strategies for architecting secure cloud networks. The OSI model is a conceptual framework that divides network communication into 7 distinct layers. Each layer represents a specific function in the data transmission process. This layered approach simplifies network design, implementation, and troubleshooting. Importantly, it helps us understand security risks and implement appropriate safeguards at each level. Starting from the bottom, Layer 1, the physical layer, deals with the physical transmission medium, such as cables and connectors. Layer 2, the data link layer, manages data transfer between devices on the same network segment. Layer 3, the network layer, routes data packets across different networks. Layer 4, the transport layer, ensures reliable end-to-end communication. The upper layers, 5 through 7, focus on application-level interactions. Layer 6, the presentation layer, handles data formatting and encryption. Finally, Layer 7, the application layer, interacts directly with software applications such as web browsers and email clients. The lower layers of the OSI model, physical and data link, are often overlooked in security discussions. However, these layers are fundamental to network communication and present unique vulnerabilities. Layer 1, the physical layer, deals with the physical transmission medium, including cables, connectors, and network interface cards. Threats at this layer are often physical in nature, such as cable tampering or unauthorized access to equipment. Layer 2, the data link layer, manages data transfer between devices on the same network segment. Common attacks at this layer include MAC spoofing, where an attacker disguises their device with a legitimate MAC address to intercept traffic. Physical security measures like locked server rooms and surveillance cameras can deter unauthorized access. Layer 3, the network layer, is responsible for routing data packets across different networks. It uses IP addresses to identify devices and determine the best path for data transmission. Routers are the key devices operating at this layer, connecting different networks and forwarding traffic based on destination IP addresses. The network layer is susceptible to various attacks, including denial of service or DOS attacks, IP spoofing, and routing protocol attacks. DOS attacks aim to overwhelm a network or device with traffic, making it unavailable to legitimate users. IP spoofing involves an attacker forging the source IP address of packets to impersonate a trusted device. Firewalls, operating at this layer, can filter traffic based on source and destination IP addresses, port numbers, and protocols. Intrusion detection and prevention systems, or IDS/IPS, can monitor network traffic for suspicious activity and block malicious packets. Securing routing protocols with authentication and encryption helps prevent unauthorized modifications to routing tables. Layer 4, the transport layer, ensures reliable end-to-end communication between applications running on different devices. It provides mechanisms for establishing, maintaining, and terminating connections, as well as for segmenting data into manageable packets and reassembling them at the destination. The 2 most common transport protocols are Transmission Control Protocol, or TCP, and User Datagram Protocol, or UDP. TCP is a connection-oriented protocol that provides reliable data delivery with error checking and flow control. UDP, on the other hand, is a connectionless protocol that sacrifices reliability for speed. Security considerations at the transport layer include protecting against TCP SYN flood attacks UDP flood attacks, and port scanning. TCP SYN flood attacks exploit the three-way handshake process used by TCP to establish a connection. UDP flood attacks inundate a target device with UDP packets, potentially overwhelming its resources. Port scanning involves probing a device for open ports, which can be used to identify vulnerabilities and launch further attacks. The upper layers of the OSI model, session, presentation, and application, layers 5 through 7, focus on application-level interactions and user experience. These layers are crucial for securing the data and the applications that use it. The session layer manages connections, allowing for data exchange and synchronization. The presentation layer handles data formatting, encryption, and decryption. The application layer interacts directly with software applications. Security threats often exploit vulnerabilities in applications to gain unauthorized access or disrupt services. The TCP/IP model, named after its two primary protocols, is a practical implementation of network communication. Unlike the OSI model, the TCP/IP model defines specific protocols and standards used in internetworking. It condenses the 7 layers of the OSI model into 4: application, transport, internet, and network access. From a security perspective, the TCP/IP model highlights the importance of securing each layer to ensure end-to-end protection. Architecting secure cloud networks requires a shift from traditional on-premises security paradigms. Cloud environments are dynamic, scalable, and often shared, demanding a different approach to security design and implementation. Here are some best practices for architecting secure cloud networks. Segmentation. Divide your cloud network into smaller, isolated segments to limit the impact of a security breach. This can be achieved through virtual private clouds, subnets, and security groups. Least privilege access. Grant users and applications only the minimum level of access necessary to perform their tasks. This reduces the potential attack surface and limits the damage from compromised credentials. Continuous monitoring. Implement continuous security monitoring and logging to detect and respond to security incidents in real time. Leverage cloud-native security tools and services for comprehensive visibility into your cloud environment. Redundancy. Design for redundancy to ensure high availability and fault tolerance. Use multiple availability zones, regions, or even cloud providers to mitigate the impact of outages or attacks. Firewalls, intrusion detection systems, and intrusion prevention systems are essential tools in a multi-layered cloud network security strategy. These tools work in concert to filter malicious traffic, detect suspicious activity, and prevent unauthorized access to your cloud resources. Firewalls act as gatekeepers, controlling network traffic based on predefined rules. They can inspect incoming and outgoing traffic, block unauthorized connections, and segment your network into secure zones. Cloud providers offer virtual firewalls as a service, providing flexibility and scalability for your cloud deployments. IDS are like security cameras for your network, monitoring traffic for suspicious patterns and known attack signatures. They provide alerts when potential threats are detected, allowing security teams to investigate and respond accordingly. IPS take a more proactive approach, actively blocking malicious traffic based on predefined rules and signatures. Building a resilient cloud network requires a multi-layered security approach that addresses threats at every level of the OSI and TCP/IP models. This involves combining preventive, detective, and responsive controls to create a comprehensive security posture. Start with a strong foundation by securing your cloud infrastructure. Implement strong access controls, encrypt sensitive data, and regularly patch vulnerabilities. Use security groups and network access control lists, or NACLs, to restrict traffic flow between resources. Next, implement robust network security measures. Deploy firewalls, intrusion detection and prevention systems, and web application firewalls to protect against a wide range of threats. Consider using a Security Information and Event Management System, or SIEM, to centralize security logs and alerts from multiple sources. Finally, prioritize application security. Mastering cloud network security is an ongoing journey, not a destination. The threat landscape is constantly evolving, requiring continuous learning, adaptation, and improvement. By understanding the fundamentals of network security, Implementing best practices and leveraging essential security tools, you can build a resilient cloud environment that protects your data, applications, and business operations. Start by assessing your current security posture and identifying areas for improvement. Develop a comprehensive security strategy that aligns with your business objectives and risk tolerance. Remember that security is not a one-time effort. It requires ongoing vigilance, monitoring, and adaptation to stay ahead of emerging threats. Stay informed about the latest threats, vulnerabilities, and best practices by following industry blogs, attending conferences, and engaging with the security community.